In this video, we are going to confront the difference between calculating variance and standard deviation for a sample as opposed to a population of data. Okay, and so that's the question of the day here. It's how is it different when you find the variance and standard deviation of a sample than finding it for the population? So what we're going to do is we're going to look at a set of data that I constructed here, and it says that the following data represents the number of minutes it took 10 juniors to run the mile in their phys ed class. So let's go ahead and assume one thing here. We're going to say that this constitutes a population of the entire class. Let's say there are only 10 juniors in this class, so that they constitute the population of the entire class. What we want to do is find the mean, range, mid-range, but also the variance and standard deviation, which are the crux of this video here. And we're going to make these things rather quick things to calculate, but I'm also going to highlight, again, the difference between calculating this for a population versus a sample using the shortcut, okay? So I also say let's place the data on a number line to visually analyze the extent of the variation. We don't really necessarily need to do that in this video. So let's go ahead and start with this. If we wanted to find the mean of this data, of course, to find the mean of these times, what we would have to do is add up all the data and divide by however many there are. And considering that this constitutes a population, okay, what we're going to do is we're going to say that, first of all, the sum of the data, we use this shortcut representation of it, but we say the sum of all of our data would be the sum of all the x. And so we will need a calculator here, and essentially we can do this very quickly. We'll just go and type this in, and we say 6.5 plus 7.5 plus, we have an 8-minute time, a 6-minute time, looks like we have an 8.5-minute time, a 6.5-minute time, 8, and then 10, and then we have a 9.5, and then finally somebody took 15 minutes to run it. So the sum of our data is 85.5 or 85.55. We want to label this, okay? This is in minutes, all right? And then we say, well, how many total data were there? We have 10 juniors. So what we're going to do is we're going to write capital N, and the reason why we're using capital N is because we had 10 total students. Now, I want to list these explicitly because when we find the mean for a population, remember we use this lowercase Greek letter mu, it looks like a curvy M with a long tail in the front. The first thing I'm going to do is I'm actually going to write it as a fraction first, and we're going to say 85.55 minutes divided by 10 students. So what this does is, and I'm just going to go ahead and write what we get here, we get 8.555, and we're going to label this minutes, but this would be the average time, and I didn't have to use a calculator on this one because we were dividing by 10. But notice that it's really easy to find the average if you just add up all the data and list that out, and then tell how many data there are, and you just divide them out. Okay, so as far as the mid-range, we can go ahead and the range, we can calculate those very, very quickly here. The range, we also use the capital letter R to represent this. We would just take the maximum time, 15, minus the minimum time. Looks like our minimum time here was somebody ran it in 6 minutes. So we'd say there's a 9-minute range, and that is the spread of our data. And let's say we also want to find the mid-range, which is the average of the min and the max. We would say that that's 6 plus 15 over 2, and so we get 21 over 2. And certainly if you wanted to, we could use a calculator here, but 21 divided by 2, you're going to get 10.5. Oops, 21 divided by 2. So we get 10.5, and we want to label this minutes. Now that we've arrived at the portion where we are going to find the standard deviation and the variance, the first thing I want to do is I want to illustrate this. We actually have a shortcut method that we use to find the variance and standard deviation for a population, but what it does is it outlines what information we need and how to use it in order to calculate these two things. And again, when you find the variance for a population, we use this lowercase Greek letter sigma squared, and we say that the standard deviation is just sigma. So what this means is we're only going to need to know how to find the variance here, and we'll just take the square root of that to find the standard deviation, okay? And that's what this formula is here. It's just the square root of this first one. So in terms of what we need to know here, there's a reason why I added up all the data and wrote that out, because there are 3 things we need to know to use this formula. We need to know n, which is how many data there are. We've already found n. Okay, when we found the average. We need to know the sum of the data, or the sigma x here, and that's this number we're going to put here in the second spot that we'll end up squaring. But the only other thing we need to know is the sum of the squared data. So just to kind of show you how simple it is to calculate the standard deviation for any set of data, you just need to know how many data there are. You need to know what the data adds up to. Keep in mind, you already have to find this when you find the average anyways. The only other value that we haven't calculated yet would be the sum of the squared data. That is, we're going to go through, we're going to square all these numbers and then add them up. And the nice thing about this is we could do this really quickly on a calculator. I'll clear all this out, but we'll just say 6.5 squared plus 7.5 squared plus 8 squared plus 6 squared plus 8.5 squared plus 6.5 squared plus 8 squared plus 10 squared plus 9.5, that number squared, plus 15 squared. I'm going to hit equals here, and we get this really big number, 792.25. So we get 792.25. What I'm here to tell you is to calculate the variance, which, by the way, again, we use this lowercase Greek letter sigma squared to find the variance. It's really easy. It's just that we need to know these values right here. So according to this formula that we're going to need to know, we're going to take the number of data, which we have here in this case to be 10, times sigma x squared. That is the sum of the squared data. You can always think of this as just being the bigger of the two numbers first. So we get 792.25. And this is going to be minus. Now we're going to take the sum of our data and square it. So in parentheses, we'll say this thing's squared, and we're going to drop in the sum of our data, which was 85.55. And in the basement here, the important thing is that we're going to take the number of data and take it times itself. So n times n. So we get 10 times, in this case, 10. So this right here, you got to know this is the variance right now. We have the variance. It's just that we need to type this into a calculator and find a value for it. So what I know is that 10 times 10 at the very least on the basement is going to be this here. And as far as what we get on the top, I'll get my calculator out here. But what we could do is we could just say, well, we got 10 times 792.25 equals, and then we're going to say minus, now in parentheses, 85.55 squared, end parenthesis, and then equals. So on the top we get 603.6975. So we get 603.6975. And when we actually take the time to divide this out, that is, in this case, we're going to say divided by 100, we get 6.036975. So we get 6.036975. Now I'm not going to round that right now, but what we can say is that this is the variance. This is the variance. And in order to find the standard deviation, okay, so standard deviation, all we need to say is that really it's just sigma, which is equal to, I'm going to write symbolically here, the square root of sigma squared. So in other words, we're going to take the square root of this number right here, which was 6.036975. And basically, I'm just going to advocate for, since we didn't erase it on your calculator, and you shouldn't erase it on your calculator, we're going to take the square root of this, and what you get is about 2.457. Now, should I round this? Yes. What I'm going to do is round to one extra place value than what the original data went out to. And I noticed that the furthest any data went out to was to the nearest tenth. So we'll go to the hundredth, and we get two spots here. We get 2.46-ish, and we're going to label this. So we get approximately 2.46 minutes. Okay, so this standard deviation right here basically says this: if the average time was about 8.5 minutes, then the average time was within approximately about 2.46 minutes of the average. Things were about that close to the average on average. So at the beginning of this video I said, well, what's the difference between calculating this for a population and calculating this for a sample? What we'll do in this instance is we're going to go back and calculate the variance and standard deviation again, except for this time we're going to assume that these are 10 randomly selected juniors in an entire high school. So what we have now is a different set of formulas. There's actually a difference in the way we calculate variance and standard deviation. What I want you to notice is all of our n's have now, notice they were capital N's over here because they were population before. All of our n's become lowercase n's to represent the fact that we're talking about a sample. Instead of sigma squared, we write Roman letter s squared to indicate that we're talking about a sample. And the only difference here is this: instead of dividing by n times n, we have to divide by n times n minus 1. So just to keep this simple, I will tell you this: we still need all of the same values. These are values we calculate all the time. We get 85.55 is the sum of our data. The sum of our squared data, the data when we squared it and added together, was 7092.25. And then in this case, we say lowercase n is 10. So nothing's different. The only thing that's different is when we write s squared now, in the basement, we're not going to get 10 times 10. We get 10 times 10 minus 1. Or in other words, we get 10 times 9. In other words, we get 90. And then on the top here, we say, well, what do we get on the top? It's the same stuff, guys. So it'll be 10 times the sum of our data squared, so 792.25, minus now the sum of our data, that thing being squared, okay? And so the only difference, and I just want to point this out again, is this: when you do this for a sample, you have to take it times n minus 1, or divided by n times n minus 1. So in this case, we'll just run through our calculations again. You're going to notice that we get the same things on top, so 10 times 792.25 equals, now minus 85.55 squared. We end up with that 603.6975, so we get 603.6975. 603.6975, and we're just instead going to take it divided by 90 in this possible instance. Okay, so we say if we take this number divided by 90, this changes our variance slightly. So our variance becomes 6.70775. So we get s squared is 6.70775. And you'll notice that this number here is slightly bigger than the variance we got over here. And so to find the standard deviation, we say that it's the square root of s squared, which is the square root of this number right here, 6.70775. And so we're going to get a slightly bigger standard deviation in this case. So if we take the square root of this number, not a hard thing to do, we get approximately 2.59-ish if we're rounding appropriately here. And we want to label this, we say, in minutes. Okay, so if the average time is about 8.55 minutes, the average data is within about 2.59 minute steps of the average. Okay, so just to follow up here really quickly here, I want to ask a few questions about this set of data, but I ask first of all, if 2 minutes were added to each time in the data set, what, if any, would be the effect upon the average, and what, if any, would be effect upon the standard deviation or the spread of our data from the average? Okay, so my guess would be this: if we added 2 to every time in this data set, everybody ran a mile time that was 2 minutes slower, then what would happen to the average? Well, the average would not stay the same, so it couldn't be this first possibility. I would think that the mean would have to increase by 2 minutes. So it wouldn't stay the same, mean increases by 2 minutes. But the question is, what happens to the spread of our data? And consider this: if everybody moves up 2 minutes, the average might move up 2 minutes, but all of the data are still equally spread apart from the mean. So what's going to happen is that not that our standard deviation increases by 2 minutes, but then it stays the same. Okay, so our average would increase by 2 minutes, and the spread of the data would remain the same. Okay, so it says which of the following times, if added to the data set, would result in the smallest standard deviation. Okay, well, the idea here is this: the closer data is to the average, the closer it is to our average, which was 8.555 minutes in either instance, then what we could say is that the data that we added in here that is closest to that would give us the smallest standard deviation. So which of these data would be closest to the average? It would be this 8 minutes right here. If we added in a 15-minuter, it would be way far apart from the average, resulting in a bigger standard deviation. And so the same thing would happen if we added in like a 4. 6.5, not as much, but 8 is the closest to the mean. And then last but not least, I asked the question, if a time of 15 minutes were added to the data set, what would be the new mean? Well, the idea here is that we could go back and calculate the new mean. We would have to add 15 on to the original sum of our data here. So we would get some new sum, and we would have to change our n from being 10 to n being 11. And this would be easy to go back and calculate. As a matter of fact, what we could do is just get our calculator here and say, well, 85.55 is what the original data set added up to. If we add in an extra 15 minutes and instead divide by 11, you can see that the average time goes up to about 9.14 minutes. But that's the difference between calculating standard deviation and variance for a population as opposed to a sample using the shortcut method. Cheers.